Hello Year 11. I'm just going to quickly go through the test review with you, just in case you find the mark scheme confusing. So let's have a look. We're supposed to be green penning the test. I suppose I'll use green pen too. So the diagram shows forces acting on the object, which is the resultant force. Well, it's 4 newtons to the right, 6 going this way, 2 going that way. They cancel each other out a little bit, and all that's left over is 4 going that way. Base jumpers, so let's have a look. The base jumper accelerates forwards when force A is bigger than force B. The base jumper falls with a constant speed when force C is equal to force D. To land safely, the base jumper opens the parachute. What effect does opening the parachute have on the speed? Well, it would decrease. Or slow down. Give a reason for your answer. Well, the whole point of the parachute is it increases drag, the drag force, or you could say it increases air resistance, or you could say the parachute has a big surface area. The easiest answer I think is it increases drag. Remember, if I'm going too quickly, just pause the video. And then you can unpause whenever you're ready. So, question 2. On the diagram, mark with an X the point where you think the centre of mass is on the life belt. Well, this life belt's symmetrical. So where's the line of symmetry? I'll get a line. Let's see if I can... Kind of wonky a bit, but let's do another line. My lines aren't very straight. But there you go. So, line of symmetry. The X should be right in the center of this ring. Why have you chosen this point? Well, this lifeboat is symmetrical. Or you could say something like the lifeboat is hanging, so the center of mass will be directly below where the hook is. But I'm going to say lifeboat is symmetrical. So the center of mass lies where lines of symmetry cross. Right, next one. Question 3. Choose the words from this list to complete the sentences below. When you drop something, it falls because it is pulled to the earth by gravity. We measure this force in units called newtons. All forces. We measure forces in units called newtons. Forces are always measured in newtons. Doesn't matter what the force is. When a falling object reaches the ground, it stops moving. This means the forces acting on it now are balanced. If something is not moving, they must have balanced forces. Right. The mass of a toy is 0.06 kilograms. Gravitational field strength equals 10 newtons per kilogram. Calculate the weight. So all I've done there is I've written that information down so it's easier for me to sort of understand. Now, you need to remember this equation. Weight equals mass times gravity. So in this case, the weight equals 0.06 kilograms times by 10, which equals 0.6 newtons. Remember, it's a force, so it has to be newtons. So the answer is 0.6 newtons. Now you would get the marks. You'd get 1 mark for the equation, and you'd get 1 mark for getting this answer here, and you get 1 mark for writing newtons. Okay. Complete the following sentences. When a toy is hovering stationary in midair, the lift force is the same as the weight of the toy. The important thing there, if it's stationary, it is not moving. If it's stationary, it's not moving. You'll have your toy like this, and if it's, that means this force here has to be equal to this force. The forces must be balanced, because if the forces are unbalanced, there will be a resultant force, which means there will be an acceleration. And right now, the resultant force equals 0 newtons because these two are cancelling each other out. What does the word accelerate mean? Easiest way, you can say change velocity or change direction. I'm going to put... It's important that you say it's change velocity because remember, if you accelerate, you either increase your speed in a straight line or you turn. So if you're in a car and the car starts going faster in a straight line, that's acceleration. Or if the car goes around a roundabout, but the speed stays the same, that is also acceleration. What is the direction of the resultant force on the falling toy? Well, if the toy's falling because it got switched off, there's less lift force now, but the weight force stays the same. So the resultant force, you see this arrow doesn't quite cancel this arrow out. They're uneven, so the resultant force is downwards. So okay. Question 5, which is the last one. Measure the extension of the spring. Now, I did this one because you had Microsoft Word, the easiest way to do it, and this is what I did here. I got the line drawer, which is up here, and I drew a line, and when you draw it, if you hold shift, it stays the same direction, so it doesn't wiggle around. So I drew my line, it's about at 10, okay. I drew my other line from here. The same point, you see I took it from this point there, so I had to take it from the same point here, just about, and there it lines up at 10 centimeters, okay, and here it lines up there. Now it says in millimeters. Now from 10 to 11 millimeters, that is from 10 to 11 centimeters, this is 10 millimeters. And then I've got 1, 2, 3, 4. So the total that I got was 14 millimeters. Now, I got this because I zoomed the paper really, really far in and I drew my lines. So I'll give you an answer that is from 13 to 15 millimeters. Okay, because it's quite difficult to read. So, the extension, I'll give you anything, I'll give you the answers 13 millimeters, 14, well actually anything in between. Anything between 13 and 15 millimeters included. So if you've got, say, 13.7 millimeters, you got the answer right. Okay. Before taking the measurements, the student adjusted their ruler to make it vertical. Why? Well, you do this, you see, okay, for the ruler's kind of slanted, so you're not going to get a correct reading. So you're going to increase the, you're going to decrease the error when you are reading your measurements. Because if you measured, say, from here to here, because your ruler is at an angle like this, and you're measuring the point from there to there, you're going to get an error. So you have to do this because it will reduce the error. Now, it's asking for another, because it's 2 marks, and it said explain why. Well, we've sort of said what's going to happen, but we've not been specific. If that ruler is at an angle, so let's say I had my ruler like this, and I had my ruler at an angle like this, you kind of know from triangles that if I have something that is like that, we know this is a hypotenuse, so this is longer, and this is the shorter side. So you should know if you tilt something at an angle, say if I had a piece, if I had my spring here that I had to measure, it might read 10 centimeters on this ruler, but because this ruler is at an angle, it could read 15 centimeters on this ruler. So you had to reduce the error, because if the ruler is at a slant, the measurements would be too large. So that was a little bit mathsy. Now, what range of weights did the student use? So if you look here, weight in newtons. Now the graph goes from 0 to 6, but let's look at the points. They have not put across at 0, but they've put across here, 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 and here. So the smallest weight that this person uses is 1, and the largest weight that this person uses is 6. So the range of weights is 1 newton to 6 newtons, or you could have written it as a mathematical range, which is the range is 5 newtons. So it went from 1 to 6, so 6 take away 1 is 5. So both of these answers are correct. I'll put a little arrow. 1 newton to 6 newtons. Why does the data plotted in figure 3 support the student's prediction? Well, it is a straight line through the origin. If something... So I'll go back to the prediction so you can see what it was again. The student said this. The extension of the spring will be directly proportional. You should know from maths that this means straight line through the origin, which is 0, 0. Okay? And as you can see here, this is a straight line that goes through the origin. So, straight line and it goes through the origin. Or it goes through 0. Describe one technique you could have used to improve the accuracy of the measurements taken by the student. Well, let's redraw what they've got. They've got a clamp here. They've got a spring. We'll do it in blue, right? The spring is in blue, right? There's a spring down like that. And then you've got a weight attached to it. So here's your weight. And you've got a ruler down the side. So ruler like that. Yeah. One way that you could make this more accurate is if you could attach something like a set square. And a set square looks like this. A set square is just a right angle. It looks like a little triangle, has a hole in the middle. You probably see them in maths, and it's got like rulers down the side like this. It's got rulers on the sides, and the whole point is it's so you can see a right angle. If you do design technology or engineering with Mr. Doughty, you've probably used one of these quite often to check that something's a right angle, but it's more often it's used in maths, again, to see if something's a right angle. So you could get one and stick it to here so that you've got so you could stick your set square like this, and you could tell, you would line one point up here, and then you would definitely know that this was 90 degrees to the right. Or I like the idea of attaching sort of a pointer. So you would glue or sellotape, or however you want to do it, a pointer somewhere on here, and your pointer would just stick out. Doesn't really matter if it's not completely perfect. Your pointer would stick out like that, and then you don't move that pointer, but when you put the weights on the spring, the pointer will always point to a certain bit on the ruler, so you know that you haven't misread the results. Another way, an obvious way, get your camera, have it on a tripod somewhere. So get your phone, this is your phone, there's I don't know, there's the camera on the back of your phone. And every time you do a result, you take a photo, or you record the video of it, so you can pause exactly, and then you can, like I did on the previous question on this one, you could actually do this. You could print the picture out and you could draw the line across. And that would work as well. And that would probably be the simplest way of doing it. Just take a photo of each time you do the experiment. So I've described them there. So I'll write, let's do attach pointer to spring that lines up with ruler. Okay. Let's go down a bit. Last question. At the end of the experiment, all of the weights are removed from the spring. What can you conclude from figure 4 about the deformation of the spring? So, well, let's have a look here. We should know that, you see, this is kind of a straight line up until this point. So this is straight. And then here it starts to curve. So when we said something was directly proportional, it's only when the line is straight. So if you remember from the other lesson, P is the limit of proportionality. So if you, what this question here is asking, if you were to take all the weights off this spring and have a look at it, what has happened to the spring? Well, you need to say the spring, it no longer goes back to its original size. So I'm using green pen, sorry. The spring, it won't go back to its original size. Original size. You can say this, something along the spring is broken, but you have to also mention the fact that the spring looked like this at the start, right? Nice and neat. And then the spring looks like this at the end. Okay, so it's been deformed. Give a reason for your conclusion. So why do you know this? Well, from this graph here, you know that the graph is now curved. You could say the graph is now curved. That is enough, but if you really wanted to absolutely secure the mark, you would need to say you've gone past P. You've gone past, so gone past limit of proportionality. Start that again. Proportionality. Or you could say the line is no longer directly proportional. And then you're done. Right, I hope that helped. And I'll see you tomorrow.